Okay, here's another classic optimization problem where there's a certain amount of printed material that needs to happen. We need to have 42 square inches of printable area. So I've kind of shown that here in the what's shaded blue, and the fact that that area needs to be 42 square inches. That obviously can't change. That's going to turn out to be what I've been referring to as sort of like a constraint on this problem. And what we're trying to do is use as little paper as possible to maintain 42 square inches of print and to have a 2-inch margin on one side and 1-inch margins on all the other three sides, as it says in the statement of the problem. So there's two different ways to approach this, and one is to kind of refer to a horizontal dimension of the paper as x and a vertical dimension as y. And then the printed stuff would be in terms of x and y. However, I feel fairly strongly that I think it's a little bit easier. The algebra gets a little easier. The calculus gets a little easier if you use this kind of dimensions of the print as x and y, and then we can talk about the dimensions of the paper. If the print was y and then we go an extra 1 inch up this way and 1 inch down that way, that'll give us a total of y plus 2 inches. And then down here on the bottom, we had x inches across here, but we went 1 out to one side and then 2 out to the other. That width of the paper would be x plus 3. And what we're trying to do is minimize the area of that piece of paper. Well, the area of that piece of paper is the width of it, which is x plus y, times the height of it, which is y plus 2. And as we've seen in a number of these other problems, you want to avoid having two variables in here. It's not completely a deal breaker, but it's easily overcome when we have to factor in our constraint in this problem, and that's the area of the print inside this blue region, which is x times y, has to be 42 inches, or 42 square inches. So xy equals 42. So probably the easiest thing to do is maybe we can solve for y and get 42 over x, and now we're going to substitute that value into our function that we're trying to optimize. So as a function of x now, we're looking at x plus 3, that quantity, multiplied by 42 over x plus 2. So that's what we're trying to optimize. And if we just take the derivative, set it equal to 0, get some critical numbers for ourselves, we'll be in business. So one thing that we can do is go ahead and kind of simplify this, or FOIL out those two binomials there, and we'll see what we get when we do that. So we'll get a little cleaner function. So the first, x times 42 over x, is just simply 42. X times 2 is 2x. The insides, we get 3 times 42 over x. 3 times 42 is like 120 plus an extra 6, so we'll say 126 over x, and then 3 times 2 is 6. We could clean that up even a little bit more and say that that's 2x plus 126, x to the negative first, plus 48, grouping our like terms of the 42 and the 6, and recognizing that 126 over x is 126x to the negative first. I've had students in the past take this equation, take an equation similar to this, and set it equal to 0. Problem is you haven't done the derivative yet, so we've done a lot of algebra, but we haven't done any calculus yet, so we want to make sure we first take the derivative, which would be 2, and then minus 126 x to the negative second. The derivative of 48, of course, is just 0. Set that guy equal to 0, and we can go about to solve this thing for our critical numbers. Now, again, this is 2 minus 126 over x squared equal to 0. So we have a critical number at x equals 0, which of course doesn't make a whole lot of sense in the context of this problem. Our domain would be x would have to be greater than 0 in order to get some area. So let's just see what we get when we solve this. We can add the 126 over x squared over to the other side, and we're going to get 126 over x squared is equal to 2. Cross multiply and divide. X squared is equal to 63. So x is the square root of 63, which is square root of 9, square root of 7. So it's 3 root 7. Now, of course, it would be plus or minus 9 root 7, but again, we can't have a negative width of our printed area, so we can disregard that. So all we know is that when you graph this thing right now, when you graph that function, it's going to have a horizontal tangent at 3 root 7, when x is 3 root 7. So in order to say, verify that that's actually a minimum, what we, a couple ways we could do it. We could set up a sign chart, but oftentimes in these problems, the second derivative test is just as effective, maybe even a little bit more effective because it's so efficient. So if we do a double prime, working with a prime right here, we get the derivative of 2, which is 0, and then negative 2 times negative 126 is positive 252 x to the negative third. And of course that means 252 over x cubed. And that's a double prime. So a double prime at 3 root 7. I have no idea what its value is going to be, but I can tell you for sure it's going to be positive. 3 root 7 getting cubed is certainly greater than 0. So because the second derivative is positive, that means the function is concave up. But we already know that the slope was 0, and if it's concave up with a slope of 0, that represents a min. So we could say, therefore, x equals 3 root 7 is a min. Now, it's asking for the dimensions of the page, so we need the whole paper thing. But maybe let's get y first. So y would be 42 over 3 root 7, just using our formula up here. See, 3 goes into 42 an even number of times. That's 14 times. That's 14 over root 7. So there's x and there's y. But to get the paper, we just have to add 3 to x. So the paper's dimensions, again, is x plus 3. So that's 3 root 7 plus 3. And then it's going to be, the y dimension is going to be 14 over root 7 plus 2, because that's the y dimension. So there's the dimensions of our paper. 3 root 7 plus 3 by 14 over root 7 plus 2. So the only way those problems get a little different is if with different numbers, but different margin lengths. But pretty much I think always the best strategy is to use the area of the printed matter to be x and y, and then the area of the paper, you're going to add the margins in each direction. So a pretty straightforward problem now.